Welcome to this explainer. Right out of the gate, we're aggressively setting the stage to track the high-yield histological gradient of the urinary system. We're going to trace the exact pathway of blood plasma, starting all the way up at the delicate, high-pressure microscopic ultrafiltration barrier in the renal cortex, and following it all the way down to the thick, muscular excretory urothelium of the bladder. Every single cellular layer we're going to cover dictates a very precise physiological function, and as you'll see, when these layers fail, specific pathologies arise.
Here's the architectural transition we'll be tackling today. 1. The renal corpuscle. 2. The reabsorptive engine. 3. The loop of Henle and DCT. 4. The JGA checkpoint. 5. The collecting ducts. And 6. The impermeable vault.
Zone 1. The renal corpuscle and filtration barrier. So let's jump right into the 200 micrometer blood filtration unit housed entirely within the renal cortex. Just look at the microscopic precision in this transmission electron micrograph. Ultrafiltration here happens through a very strict three-part structure. First up, the fenestrated capillary endothelium, which physically blocks blood cells. Second, you have the incredibly thick 300 to 360 nanometer glomerular basement membrane, or GBM. This is actually formed by the fusion of the capillary and podocyte basal laminae, and it's densely packed with cross-linked type 4 collagen and laminin to restrict large plasma proteins. And third, we have the visceral layer containing podocytes with their interdigitating secondary processes, which we call pedicels. Now, bridging the 25 to 30 nanometer filtration slit pores between those interdigitating pedicels are these specialized zipper-like slit diaphragms. But the absolutely crucial point here is the presence of podocalyxin. This is a vital polyanionic glycoprotein located right within those slit diaphragms. It actively creates a negatively charged molecular mesh. Why does that matter? Because it ensures that even small organic anions and negatively charged proteins are aggressively repelled back into the capillary lumen. It's a brilliant design. And you know, this brilliantly illustrates exactly why understanding this histology matters so much in the clinic. When this filter gets disrupted, we see massive proteinuria, which is classic of nephrotic syndromes like diabetic glomerulosclerosis. That disease causes a pathological thickening and progressive failure of that glomerular basement membrane. On the flip side, nephritic syndromes involve active inflammation. Though Goodpasture syndrome, where autoantibodies directly attack the type 4 collagen in the GBM we just examined, or glomerulonephritis, which involves the deposition of circulating antibody-antigen complexes right within the glomeruli. Okay, so filling the interstices between the capillaries that lack podocytes are the mesangial cells. These are essential parasite-like cells. Notice how these cells provide physical capillary support, but they do more than that. They also actively phagocytose trapped protein aggregates and antibody-antigen complexes that get stuck on the filtration barrier. Plus, by utilizing their contractile properties, mesangial cells can actually adjust their contractions in response to blood pressure changes, helping to maintain an optimal glomerular filtration rate.
Zone 2. The reabsorptive engine, or the proximal convoluted tubule.
We're now following the filtrate out of the capsular space and into the proximal convoluted tubule. And wow, this ultrastructure perfectly connects histology to extreme metabolic demand. The PCT is lined with simple cuboidal epithelium, specialized for intense active transport. It normally reabsorbs 2/3 of filtered water and literally all organic nutrients like glucose and amino acids. To pull that off, notice the massive, prominent apical brush border of long microvilli, completely maximizing the absorptive surface area. Basally, you can see deep membrane invaginations packed tightly with long mitochondria. Those mitochondria are there to supply the localized ATP required to relentlessly drive transcellular active transport pumps. But because of this relentless ATP demand, the PCT is highly vulnerable to ischemia and toxins. In fact, it's the primary site of injury in acute tubular necrosis, or ATN.
Zone 3. The loop of Henle and distal convoluted tubule.
Now we're tracking the filtrate as it leaves the cortex and dives deep into the medullary pyramids to build a hyperosmotic interstitial gradient. And the histology radically shifts right here. The thin descending and ascending limbs transition to a simple squamous epithelium containing very few organelles. This specific design is strictly for the passive permeability of water and ions. But in stark contrast, as the loop returns toward the cortex, it becomes the thick ascending limb. Here it reverts to a simple cuboidal epithelium, dense with mitochondria again, specifically to drive active ion transport out of the tubule and into the interstitium. This is actually the precise, high-yield pharmacological target for loop diuretics like furosemide. Following this, the distal convoluted tubule continues with simple cuboidal cells, but it lacks a prominent brush border, which gives it a much clearer, wider microscopic lumen.
Running perfectly parallel to these loops of Henle are the vasa recta capillaries. Blood flow here operates as a countercurrent exchange system to maintain that hyperosmotic medullary gradient. But because the vasa recta extends so deep into the medulla, it naturally has very low oxygen tension. And this creates a high-yield clinical vulnerability, sickle cell nephropathy. Affected erythrocytes will sickle in this low oxygen vasa recta environment, obstructing blood flow and resulting in devastating renal infarcts within the renal papilla and pyramids.
Zone 4, the regulatory checkpoint, the juxtaglomerular apparatus.
We now ascend back into the cortex to analyze the juxtaglomerular apparatus, which is a critical autoregulatory sensor. This specialized structure forms exactly where the distal tubule contacts the vascular pole of its parent glomerulus. It's essentially a cellular trio. First up, the macula densa. These are columnar, closely packed cells in the distal tubule acting as osmoreceptors to constantly monitor sodium and chloride levels. Second, we have the juxtaglomerular, or JG cells. These are modified smooth muscle cells in the tunica media of the afferent arteriole that have shifted to a secretory phenotype, so they're absolutely packed with running granules. Finally, the extraglomerular mesangial cells, or Lacey cells, sit right between them, providing supportive functions.
So what actually happens when systemic blood pressure drops? Well, local baroreceptors trigger the JG cells to secrete the aspartyl protease renin directly into the blood. Renin then cleaves plasma angiotensinogen into angiotensin 1. Next, angiotensin-converting enzyme clips it into angiotensin 2. Now, angiotensin 2 is a potent vasoconstrictor, and it simultaneously stimulates the adrenals to secrete aldosterone. Aldosterone then acts on the distal tubules to promote sodium and water reabsorption, essentially rescuing blood volume and pressure.
Zone 5, collecting ducts and acid-base balance.
The filtrate now enters the collecting ducts located in the medullary rays. You really need a solid high-yield mental model for differentiating these ducts. They basically contain two distinct cell types. The vast majority are the pale-staining principal cells. These cells sequester aquaporin channels in cytoplasmic vesicles. When the body is dehydrated, antidiuretic hormone, or ADH, binds to these principal cells, which stimulates the insertion of these aquaporins into the apical membrane, allowing for massive regulated water reabsorption. They're also the pharmacological target for potassium-sparing diuretics like spironolactone. Scattered among them are the slightly darker staining intercalated cells, which are packed with mitochondria. These actively secrete either hydrogen or bicarbonate ions, acting as the ultimate regulators of blood acid-base balance.
Zone 6, the impermeable vault, the urothelium.
At this stage, the fluid leaving the papillary ducts is no longer being modified. It is officially urine. From the minor calyces through the highly muscular peristaltic ureters and into the bladder, the excretory passages are lined by a uniquely stratified tissue called urothelium, or transitional epithelium. It consists of a single layer of small basal cells, an intermediate region of cuboidal cells, and a superficial layer of massive, highly differentiated cells. Its singular purpose is to act as an impermeable osmotic barrier, protecting the underlying tissues from the cytotoxic effects of hypertonic urine. The true protective stars of the urothelium are the superficial umbrella cells. These things are massive, reaching up to 100 micrometers in diameter. Their apical membranes are asymmetric unit membranes packed with paracrystalline arrays of incredibly stiff integral membrane proteins called uroplakins. When the bladder empties, these rigid plaques hinge and fold inward, being internalized as discoid vesicles. But as the bladder fills and distends, these vesicles rapidly rejoin the apical membrane, dramatically increasing the surface area without ever breaking the tight junctions or compromising the osmotic barrier. It's a phenomenal structural adaptation. Of course, downstream pathologies can directly impact this excretatory network. For example, calcium salts or uric acid can precipitate in the renal pelvis to form renal calculi, otherwise known as kidney stones. These can become lodged in the muscular ureters, agonizingly obstructing peristalsis. The urinary tract is also highly susceptible to acute pyelonephritis, where bacterial infections ascend directly from the calyces right into the associated renal papilla. Plus, the prolonged exposure of this tissue to concentrated urinary carcinogens, like those from smoking or occupational exposures, forms the primary pathogenesis for high-yield urothelial carcinomas. Okay, let's step back for a macro summary. Think about the incredible architectural transition we just traced. We started out at the delicate, high-pressure, incredibly leaky cellular filtration barrier of the renal corpuscle, which operates in a matter of minutes. We then moved through the dense, mitochondria-rich reabsorptive tubules pulling back water and nutrients over hours. And finally, we arrived at the thick, muscular, entirely impermeable macroscopic vault of the bladder, designed exclusively for safe storage.
I want to end this explainer with a high-yield question to really lock in your understanding of the structure-function relationship. What unique structural component of the renal filtration barrier is the ultimate target of destruction in end-stage diabetic kidney disease? Think back to the ultrafiltration barrier we started with, visualize the layers we discussed, and consider how systemic microvascular disease compromises that vital mesh. Hold on to that answer and definitely use it as a primer for your next pathology review.